So now for this simple rational function, the bend in the graph is something you can probably guess, but let's complete step 4 to be sure. Checking my space. Ooh, can we fit that in? I am not going to try. Oopsie, sorry. We're over here. I'll just quickly make a new page. And then zoom it a little bit. So here's going to be where we're at. Our first derivative that we want to use will probably be this guy. So next we want to do step 4, which is concavity, where I have to find the second derivative. And I'm going to look at the most convenient version of the first derivative. I just took the negative back in, so up here. And it's going to be the quotient rule, and it's going to be a little messy, but it is the way it is for this type of function. So I have my bottom one squared. So let's start with that. So it's x squared minus 4. It was squared. Now another squared means to the power of 4. Then it's going to be the derivative of the top, which is negative 2x, times the bottom, which is this bracket squared, minus the top, negative x squared minus 4, times the derivative of the bottom, which is going to require a little chain rule, 2 times the bracket to the power of 1, times the derivative of the inside function, and there is our quotient rule done. Now it's a matter of cleaning up the top here. I'm going to leave the first term the way it is, and just see what I can do with the second one. I'm going to take this minus into that first bracket and put the 2 and 2x together. So then it becomes x squared plus 4, and the other x squared minus 4 is still there, over x squared minus 4 to the 4. Now see how these guys are all the same. So I can take, in the top, one of them out as a common factor, be left with negative 2x times the other bracket, because there were 2, plus 4x. This bracket is still there. This bracket is now out. And still, the denominator is the same. Now I can cancel one of them with one of those, leaving 3, and simplify the top, multiplying the negative 2x in for negative 2x cubed, and plus 8x, this one in, negative 2x cubed, this one in, positive 8x. And the 4x in gives me 4x cubed, and plus 16x. Same denominator. Nothing changes there right now. Then I have 2x cubed terms, which I'll put together as 2x cubed, and these two together will be 24x. Same denominator. It's very easy to make a little mistake here. Please be very careful. Now I can take out a 2x and be left with x squared plus 12, which is a plus, so it's not going to factor. I can, however, factor the bottom at this stage because I am done there are 3 of each of these. And there is my second derivative. Now, let's look at our 2 checks. Second derivative is 0 when? Well, either one of these in the numerator is 0. One of them is an x, so that can be 0. But this is x squared plus 12, and that can never equal to 0. Otherwise, x squared is equal to negative 12, which is impossible. So only 1. And the second derivative is undefined when the denominator is 0, and I get my 2 and negative 2 again. So I have 3 potential inflection points. Now I'm going to make my table, and it's split up according to negative 2, 0, and 2. And I list all the pieces on the left. I'll keep 2x together, x squared plus 12. And this time I'm going to put these guys together, but feel free to split them up. Together, one way or another, it gives me my second derivative. So I have now 4 intervals, 4 pieces to consider. 2x is 0 when x is 0. It is in the numerator, makes the whole thing 0. It's going to go negative to positive. X squared plus 12 is never 0. It's always positive. X plus 2 is 0 when x is negative 2. It is in the denominator, makes the second derivative function undefined. It's going to go negative to positive. Please make sure that you know why. X minus 2 is 0 when x is 2. In the denominator, makes the second derivative function undefined. It's also going to go negative, oops, that was a negative, to positive. So now, in the first section I have 3 negatives, then I have 2 negatives, then I have 1 negative, then I have no negatives. So I'm bending down, up, down, up. Let's write them down here. F is concave up on negative 2 to 0. Which one should be included? Not negative 2, because my original function is not happy with negative 2, but it is happy with 0. And it's also concave up from 2 to infinity. And again, my original function not defined at 2. F is concave down on negative infinity to negative 2, not including 2, functions not defined. 0 to 2, not including 2, but I am including 0, the function is defined there. Which of these guys are critical points? Not critical, I'm sorry, inflection points. Well, I have to be a point. So that rules out 2 and negative 2. So my only contender is 0. Do I have a y value when x is 0? Yes, I do. It is 0. So this point is an inflection point, 0, 0. Just happens to be the y-intercept. So I'm bending down, then I'm bending up, down, up. And we have enough to fill in to make our graph. I'm just going to make a better looking one over here, but you can of course update it as you want to. So I have my 2 vertical asymptotes, 2 and negative 2. I have my y-intercept, and I know for the left section, it's going to be in this bottom left corner over here, like so. Trying to not be too wobbly. I'll do the right one next, up here, top right. It's going to be straightforward, a familiar shape that I've seen in rational functions already. Now, let's just have a look at what happens. I have to come towards 0 from the top, bending down, and changing to bending up. The temptation here is to maybe go horizontal, like so. It's like an x cubed type shape. But have a look at the first derivative. The first derivative is not 0 at x equal to 0. In fact, if I plug it in here at 0, what am I going to get? First derivative at 0. It's going to be -4 over -4 squared. It's not 0. It's -4 actually. So that means I have to come through this 0 point correctly. So I'm gonna come at it at an angle. A little wobbly, I know, that's my pen. Not horizontal through there. So a couple of things to have a look at. It's a fairly familiar function, quotient rule, but the quotient rule can get quite messy, so it's important to go slow and steady to get my eventual graph. Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.